Good morning to all of you. We will continue with our discussions on magnetostatics. Remember, in the last class we had discussed about magnetic fields produced by various current configurations, and towards the end we started looking at magnetic field produced by a very important element which is called the solenoid. So, let me recall, a solenoid consists of an object, a circular, usually it is a circular geometry, and you have a wire which is wound very closely around the cylindrical structure and which carries a current through the coil. So, if I draw the arrows, so the current may be flowing like this. The same current flows through the entire all the wires of the solenoid, and as we have already seen, each current carrying coil in this will produce its own magnetic field, and the total magnetic field produced by this solenoid will be the sum of the magnetic field produced by all the current elements of the solenoid. So, we started looking at using Ampere's law to obtain the magnetic field produced by such a solenoid. So, we will consider an infinitely long closely wound solenoid. Closely wound implies that the loops are circular in shape, but the loop is almost like in a plane. It is actually like a helix, it goes like this, but if they are very closely wound, I can consider each circle to be like a circular loop of wire, and I can neglect the dependence of current on the horizontal direction, and so the current flows through these loops and producing a magnetic field. So, we used first symmetry arguments to show that magnetic field cannot have any dependence on this coordinate. That means, it has to be the same at this point, at this point, at this point, inside the solenoid, outside the solenoid, everywhere. For the same position, there is no change in magnetic field as you move parallel to the axis of the solenoid. Also, if the windings are very close, then there can be no dependence on the angle of the. So, if I draw the solenoid like this here, and the coils are carrying current like this here, then there can be no dependence on this coordinate and there can be no dependence on this coordinate. That is, as you go around the solenoid, the magnetic field must remain the same if the winding is very close. That is not true if the winding is not very closely spaced coils, but in the general situation I will assume that the coil is very closely wound, which means that the magnetic field is independent of this coordinate, magnetic field is independent of this coordinate, and so magnetic field can only depend on the distance from the axis of the solenoid, which I call r. That is the only dependence on the magnetic field. Now, what about the components of the magnetic field? So, magnetic field will have components which are, one component can be along this direction, one component will be along this direction, and one component will be along the azimuthal direction. So, if I look from the top, this is my solenoid. So, there could be a component like this, there could be a component like this, and there could be a component in this direction. Now, we have used Gauss's law for magnetic fields and showed that this component has to be 0, P r has to be 0. We used Ampere's law using an Amperian loop circling the solenoid and showed that this component is also 0. The only component that will survive is a component which is along the axis of the solenoid. The only component that survives is along the axis of the solenoid. So, if I call the axis of the solenoid as z axis, the only magnetic field component that survives is the Bz component, the z component of the magnetic field. Z axis is the axis of the solenoid, and so the only component that survives is Bz. So, through symmetry arguments and through using Gauss's law for magnetic fields and through using Ampere's law for magnetic fields, we have been able to deduce some very general characteristics of the solenoid, and that we find finally that there can be only one component of magnetic field, which is Bz. Z is the axis of the solenoid, symmetry axis of the solenoid, and that can only depend on the radial coordinate, the distance from the axis of the solenoid. Now, using this we try to calculate how does the magnetic field vary with distance. So, we will now calculate what is the magnetic field produced by the solenoid. So, for that let me draw the solenoid here. So, I have the solenoid here, the current elements are coming up here, sorry, going down into the page, and the current is coming up towards me on the left side. So, the current is flowing like this, and this is my z axis. Now, what we have shown is that the magnetic field can only have a z component. Magnetic field can only have a z component, and it can depend only on r, this distance. It cannot have a dependence on z, it cannot have a dependence on this angle, it can only depend on r. So, now I want to use Ampere's law to find out the magnetic field inside and outside the solenoid. So, what we do is the following: I take an Amperian loop. So, this is, let me draw the coil here. So, these are the current carrying conductors, current coming out towards me here on the left side, and current going into the page on the right side. Okay, so, this is the z axis. So, I take a loop here lying outside the solenoid. So, let me call this A, B, C, D. So, this is my Amperian loop. So, according to Ampere's law, so let me call this distance r1 and this distance r2. So, according to Ampere's law, integral B dot dl is equal to mu naught I enclosed. So, if I take an Amperian loop and integrate over that closed loop, then integral B dot dl must be equal to mu naught I enclosed. For this loop A B C D, current enclosed is 0. So, this must be equal to 0. So, what I get is A to B dot dl plus B to C dot dl plus C to D dot dl plus D to A dot dl must be 0. So, this integration from A to B, B to C, C to D, D to A, that is a complete closed integral. Now, as we have already seen that B can only have a z component, that is a component along this direction, this is my z axis here. So, if you look at the path BC, dl vector is like this, B vector is perpendicular to BC. So, B dot dl must be 0 along this path. So, this is 0. Similarly, in the path D to A, the dl element is along this direction and B vector is perpendicular to this direction. So, B dot dl is 0 from D to A. So, the only two integrals which survive are A to B and C to D. Now, also note that when I integrate from A to B, I am not changing the distance from the axis, I am only changing the position of z, and we have already seen that the magnetic field is independent of my position along the z axis. So, the magnetic field must be the same from A to B and similarly from C to D. So, what I get is essentially integral A to B dot dl plus integral C to D dot dl is equal to 0, and this tells me B at r1 into integral A to B dl plus B at r2 integral C to D dl must be equal to 0. That means, B at r1 integral A to B dl must be equal to B of r2 integral d to c dl. So, I have changed the direction of integration. So, a to b and d to c integration are over the same length. So, this implies b at r 1 is equal to b at r 2. So, what it implies is the magnetic field is independent of the distance of this point from the axis of the solenoid. So, magnetic field here is the same as magnetic field here. Now, if I let r 2 to infinity, then the magnetic field must go to 0 as I go at infinite distance from the solenoid. So, for r 2 tending to infinity, B of r 2 tends to 0, and because this equation is independent of r 1 and r 2, B must be equal to 0 for points outside the solenoid. Please note here, I have shown through the Ampere's law that the magnetic field at this distance r 1 must be equal to the magnetic field at a distance r 2. That means, magnetic field must be independent of the distance from the axis, because r 1 and r 2 are arbitrary. I have not chosen any space, as long as both r 1 and r 2 lie outside the solenoid, magnetic field at r 1 and magnetic field at r 2 are equal. So, magnetic field must be independent of the distance from the axis outside the solenoid, and in the limit r 2 tending to infinity, I know that the magnetic field will tend to 0, and so magnetic field must be 0 everywhere outside the solenoid. Magnetic field must be 0 everywhere outside the solenoid. Now, I must still calculate the magnetic field inside the solenoid. So, for that what I do is the following: I take again the same solenoid here, the current element, the current is coming towards me on the left side, current is going inwards on the right side. Now, I take a loop which lies partly inside and partly outside. A, B, C, D. Now, let me assume that this length is L. Now, let us see the again I want to use this integral P dot dl is equal to mu 0 I enclosed. Now, we define a quantity for the solenoid, the number of turns per unit length. That means, when I wind a solenoid, I have a lot of windings, and I take a unit length and measure the number of windings, and that tells me how many windings are there in the solenoid. So, if you know the number of turns per unit length, and if you know the length of the solenoid, you can find out how many is the total number of turns in the solenoid. So, this is a quantity which I will need. So, number of turns per unit length. So, in a length L, the number of turns will be, in this, the number of turns here will be n times L. And each turn carries a current I. So, total current enclosed by the loop is equal to N L I. Each loop carries a current I, and there are N L loops within this. So, this path encloses N L loops. So, the total current enclosed is N L I, and so I get the Ampere's law tells me the integral B dot dl must be equal to mu 0 N I into L. Now, let me look at this path. So, I need to calculate the left hand side. To get the magnetic field, I must be able to integrate and get the left hand side. So, for this let me look at it. Now, this integration is from A, B, C, D. Now, as before, the integral along B, C and AD will vanish, because magnetic field has only a z component and my integration path is perpendicular to z axis. I also know that magnetic field outside is 0. So, the integration over C to D will also vanish, and the only integral that will survive is from A to B. And because magnetic field is independent of the position along A to B, I will simply get this integral will become B times integral dl from A to B is equal to mu naught n I into L. Now, integral dl from A to B is nothing but this length A to B, which is L. So, B times L is equal to mu naught n I into L. This implies B is equal to mu naught n I. And I can write the magnetic field vector as mu naught n I into K cap, where let me draw the solenoid again. So, this is my z axis and the coils are carrying current like this. These are the coils. Closely wound solenoid coils, and the current is flowing like this. So, interesting to see that the magnetic field has no dependence on R within the solenoid. It is equal to mu naught n I, point along the z direction, and it is completely uniform. So, magnetic field within the solenoid at any point is the same, but please remember we have calculated this magnetic field for an infinitely long closely wound solenoid. It depends on the permeability free space, the number of turns per unit length, and the current passing through the wires. The same current is passing through all wires, and so it creates a uniform magnetic field within the solenoid. So, this is equivalent to a capacitor, parallel plate capacitor in electrostatics, where if you had a parallel plate capacitor, we know that the electric field between the plates of the capacitor is uniform, and if you have a large area capacitor, then towards the center the magnetic field, the electric field is uniform. Similarly, here if you had a very long solenoid, towards the center the solenoid will behave as if it was infinitely long, and your magnetic field will be uniform and parallel to the z axis. So, that is a very interesting relationship we have got from using Ampere's law and some symmetry arguments. And remember, here we did not have to do any integration, any complex integration which will be involved in using Biot-Savart law. But of course, this has been done for an infinitely long solenoid. If you have a finite length solenoid, things change. So, let me calculate, it is possible to calculate the magnetic field along the axis of a finite length solenoid using Biot-Savart law, and let us do that. And I want to show you that at the edge of the solenoid the magnetic field is half of this number that we have got here. So, let me look at a finite a solenoid now. So, let me draw the solenoid here. This is the cross section. So, the current is coming towards me here. Going in. To my z axis. So, as you can see, the current is flowing like this, and the magnetic field will be towards z axis here. So, here I will calculate the magnetic field at this point at the end of the solenoid of a solenoid which has a certain finite length. So, let me call the length of the solenoid as capital L, and I will leave it here to calculate the magnetic field inside the solenoid. I will put a problem a little later. Okay. So, I want to use the Biot-Savart law to calculate the magnetic field along the axis of a solenoid. Now, I will use this following expression that we had obtained before, that remember we had obtained this formula. So, if I had a circular loop of wire carrying a current I, the magnetic field along the axis B vector is equal to mu naught I by 2 if radius of the wire is r, and if there are n turns I will get mu naught I into n into r square by r square plus z square raised to 3 by 2 k cap, where this distance, this is the point at a distance z from the axis, from the center of the circular loop of wire. The loop there are n loops here, very closely wound n loops, each wire is carrying current I, and I am calculating the magnetic field along the axis of this loop. So, I can use this formula because actually a solenoid consists of a large number of loops placed at different distances. So, for example, at this point these loops will produce a certain magnetic field, this loop will produce another magnetic field, this loop will produce another magnetic field, but on the axis all the magnetic fields produced by all the current elements are parallel and along the z axis. So, it is very easy for us to do an integration because I just need to do an addition of the magnetic fields. So, for this what I do is the following: I consider a small element of the solenoid between z and z plus dz. I consider an infinitesimal length of the solenoid lying between z and z plus dz, and so the number of turns will be number of turns per unit length into dz. So, here n is the number of turns per unit length. So, in the length dz, the number of turns will be dz, n times dz, and this distance is z. So, I am calculating the magnetic field at this point. So, magnetic field at this point will be, so let me call this dB, will be equal to mu naught I into n dz, number of turns, divided by 2 into, if the radius of the solenoid is a, I will have a square by a square plus z square raised to the power 3 by 2 k cap. So, what I have done is I have used this formula. This is the formula for the magnetic field produced at a distance z from the axis of a closely wound loop of n turns of radius r, and here my number of turns for this solenoid of length dz is actually n times dz. So, I have replaced the number of turns here by n times dz, and I have replaced r by the radius of the solenoid. So, the total magnetic field V will be equal to mu naught n I by 2 a square into integral dz by a square plus z square 3 by 2 and k cap as a constant. And remember, now the integration over z from z is equal to 0, I am calculating the magnetic field at the edge of the solenoid of a certain length L. So, integral goes from 0 to L. Now, this is a straightforward integration. All I have to do is to replace z is equal to a tan theta. So, dz is equal to a secant square theta d theta, a square plus z square will be equal to a square secant square theta. So, this integral dz by a square plus z square raised per 3 by 2 will be equal to integral a secant square theta d theta by a cube secant cube theta, and so this is nothing but secant square theta cancels off, 1 by secant theta is cos theta. So, I get this is equal to 1 by a square integral cos theta d theta, which is nothing but 1 by a square sin theta between two limits of integration. So, the limits of integration here I must calculate. So, the limits were from z is equal to 0 to L. So, z is equal to 0 corresponds to theta is equal to 0, and z is equal to L corresponds to theta is equal to tan inverse L by A. Z is equal to 0, the lower limit of integration corresponds to theta is equal to 0, and z is equal to L corresponds to tan inverse L by A. So, this is nothing but 1 by A square sine of tan inverse L by A. So, I can substitute this value of the integral in this equation and get the magnetic field B as mu naught n I by 2 A square into 1 by A square sine of tan inverse L by A, which is equal to into k cap mu naught n I by 2 sine of tan inverse. So, that is the magnetic field at the edge of the solenoid on the axis, which we have precisely obtained from using Ampere's Biot-Savart law. Now, if length is very large compared to radius, then L by A becomes very large and tan inverse of a large quantity is pi by 2, tan inverse infinity is pi by 2. So, tan inverse of a very large quantity is close to pi by 2 and sine pi by 2 is close to 1. So, I get B at z is equal to 0 is approximately mu naught n I. So, if I had a solenoid like this, very long solenoid, then at this point B is mu naught n I by 2 and deep inside, the solenoid is very long, then deep inside here the magnetic field will be mu naught n I. So, the edge of the solenoid, this is on the axis. For an infinitely long solenoid, the magnetic field is uniform right across. So, let me draw a figure which will show you an approximate picture of the magnetic field lines of a finite solenoid. So, here is the solenoid. So, let me draw the current carrying loops like this. So, this is all current closely bound solenoid finite length. So, if I were to draw the magnetic field lines, they will look something like this. So, the magnetic field and then you have some fields coming out like this and some weak fields coming out like this. So, that is a typical field within a solenoid. So, these lines will go like this here. So, as you can see here, the magnetic field lines are essentially pointing along the axis of the solenoid almost and being uniform within this solenoid. So, what we have seen is for a to calculate the magnetic field using Biot-Savart law, we could do it on the axis of the solenoid. Off axis it becomes quite complicated. At the same time, we could use Ampere's law for an infinitely long closely wound solenoid and get the magnetic field inside. And so, most typical solenoids can be approximated as reasonably long solenoids, and the magnetic field that we have got as mu naught n I by 2, mu naught n I is a reasonably accurate value. So, let me take an example. So, let me take a solenoid of length 20 centimeters, radius A 3 centimeters and number of turns is equal to 500. So, total number of turns, this is the total number of turns. So, and current 5 amperes. So, the number of turns per unit length which is equal to 500 by 20, which is equal to 25 per centimeter, and B is equal to mu naught Ni, which is equal to 4 pi 10 to the minus 7 into 2500 turns per meter multiplied by 5 amperes, which is about 0.016 Tesla. So, this is close to the center, because the length is 20 centimeters, much bigger than the radius 3 centimeters. So, close to the center the magnetic field will be 0.016 Tesla or 16 millitesla, while at the edge of the solenoid it will be about half of this value, and outside it will keep on decreasing as you move away. So, that gives you a typical figure, an expression for the magnetic field, and gives you a number, numerical value of the kinds of magnetic fields we can obtain by passing current through the solenoid coil. Now, I want to take another example, which is called a toroid. So, a solenoid is a straight device, a toroid is another device in which I have a current carrying loop which is wound along the, it's a cylindrical this thing which is closing on itself, and it is called a toroid, and there are closely wound winding turns here. So, current enters from here and leaves out from here. So, that is a toroid. If the radius becomes very large, if the radius of the toroid becomes very large, it is almost a straight, it becomes towards an infinitely long solenoid. Now, we can again use symmetry arguments to show that the only component of magnetic field that will survive is the component along this direction. So, that means only this component of magnetic field will survive. So, here magnetic field can only be in this direction, magnetic field here can only be in this direction, if at all. So, there are other components like this component, and the radial component just vanish, and once I have this, I can actually use Ampere's law to calculate the magnetic field within and outside the toroid. So, if I take for example a loop, so let me draw the toroid in one plane here, that is the plane, and so let me take, so this is my toroid. So, there are coils coming towards me, there are current conductors here on the outside of this structure and on the inside of the structure. Okay. So, let me take a path which looks like this, and there are one path, another path, and a third path. So, this is I call path 1, path 2, and path 3, 3 paths. Now, you can see that for path 1, integral B dot dl must be 0, because path 1 does not enclose any current carrying conductor, and if the magnetic field has only this component and my integration is along this direction, this must be equal to nothing but B times, if the radius is r1, B times 2 pi r1 is equal to 0, which implies B is equal to 0. Because magnetic field has only this component and is independent of the position along this circle, I can take, I will get B dot dl is equal to B dot this distance, and I can take B out of the integral, and I get an integral like this. And so, magnetic field inside, no matter where you are inside, that is in this region, in this complete region within the toroid coils here, magnetic field is 0. Similarly, in path 2, integral B dot dl is equal to, now look here, there are coils which are with currents enclosed. So, let me assume the current is coming out towards me here and current is going in here. So, you can see here that the number of turns here and the number of turns here are exactly equal. So, the net current and all the coils are carrying the same current. So, net current enclosed by path 2 must be 0. There are equal number of current carrying conductors which are coming towards me as many as going inside. So, the net current passing enclosed by this loop is 0, and again because I can integrate this and get B times 2 pi r2 is equal to 0. When r2 is this radius, I get B is equal to 0. So, inside and outside the toroid, the magnetic field is 0. I can integrate for the path 2 which is inside the for the path 3 which is inside the solenoid. Integral B dot dl mu naught I enclosed which is equal to mu naught times. Now, if the total number of turns is n subscript t, I will get n subscript t into I, where n subscript t is the total number of turns in the toroid. And again as before, because B has only this component and if the radius of this path is r, I will get B times So, there is a small dependence of magnetic field on the distance from the axis of the toroid from this point center of the toroid, but if the diameter of the toroid is small compared to this radius, then the variation in small r is very negligible in this distance and this is almost a constant magnetic field within this. Also note that if capital R, if this radius becomes larger and larger, then within the solenoid this distance is negligible compared to capital R, and this will tend to nt by 2 pi r is the number of turns per unit length. 2 pi r is the circumference of the circle here and nt is the total number of turns, and this reduces to the magnetic field of an infinitely long solenoid, as it indeed should if the toroid becomes of infinitely large radii. So, these examples have shown us the application of Ampere's law to calculate magnetic fields in some important situations, and as we have seen, whenever there is a symmetry in the system, I can use symmetry arguments to estimate the dependence of magnetic field on position and whether which components of magnetic field will survive. So, there are two points here. One is B vector dependence on the 3 coordinates and which components of B vector survive in the given configuration. Now, if the structure does not have symmetry or is a finite length etc., it becomes much more complicated, then I would have to use an actual integration using Biot-Savart law to calculate the magnetic field as a function of position. So, Ampere's law is very useful in many situations, and in many situations we can get an approximate value for the magnetic field using Ampere's law. Now, having discussed how to generate magnetic fields and how to calculate magnetic fields generated by current carrying conductors in different configurations like a straight current carrying conductor, a circular loop of wire, a solenoid, a toroid etc. Now, I want to move to another very important aspect, which is motion of charged particles in magnetic field. So, how does suppose I have a region containing a magnetic field, and if I have a charge inside the magnetic field moving at a certain speed, what is the path taken by the charge, what is the direction of motion etc. Now, let us recall we had shown that the magnetic force on a charged particle is q v cross b. So, let me draw the figure again here. So, if this is the magnetic field direction and this is the v direction and the charge is a positive charge q, the force is in this direction. So, we have to use the right handed screw rule to calculate the direction of the force. If the charge is positive, the force is in the direction of v cross b. If the charge is negative, the force is in the direction of minus v cross b. So, here with the positive charge particle, the force is along this direction, and please remember the force is always perpendicular to both the velocity and the magnetic field. Very different from the case for a electrostatic field, where the force was in the direction either towards along the direction of electric field or opposite to the direction of electric field. So, if you have a charge moving in a region which has both electric and magnetic fields, the total force will consist of the electrostatic force plus the force due to the magnetic field. So, that is a more general relation for force acting on a charge. If the charge is at rest, of course, then the only force is the electrostatic force. So, even if there is a magnetic field within the region, if the charge is at rest, it has no magnetic force. If there is no electric field, there is the only force that acts is the magnetic force, which is q v cross b. So, suppose I take a region containing a uniform magnetic field and have a charge which is moving in that magnetic field. The force, because of the magnetic field, is always perpendicular to the velocity. So, the force cannot change the speed of the particle, because the force is always perpendicular to the velocity vector. The force cannot change the speed of the particle. It will accelerate the particle, but not change its speed. Please remember, acceleration is a vector and it depends on the rate of change of velocity with time, and that can there can be acceleration without changing in speed. That is what will happen here. And so, if you have a magnetic field, let me say for example in this region, which is going into the page here, uniform magnetic field going into the page. So, if I have a particle which is a positive particle which moves like this. So, the force, it will be v cross b. So, v cross b downwards. So, the force will be upwards. So, it will change the direction of motion of the particle like this, and every time the force will go like this. So, the particle will execute a circular motion. The force is always perpendicular to the velocity vector. So, the charge particle is moving like this, here the force is like this, here the force is like this, here the force is like this. So, I have a region of uniform magnetic field, and I launch a particle inside the region with a uniform with a positive charge, and the magnetic force will make it curved and move in a circular path, and the force which will act on this will be F is equal to q v into b. V and B are perpendicular. So, the force is q v b, and let me put the magnitude here. The force direction depends on the magnitude of the force is simply magnitude of. So, this force will make the particle move in a circular path, and this force is towards the center of the circular path, and so this is the centripetal force. Is equal to, we know that centripetal force is mv square by r. R is the radius of the path. So, this force, centripetal force, is provided by the magnetic field. So, I must have mv square by r is equal to mod q into b, which gives me radius as mv by q times. So, that is the radius of the charged particle which is circulating around this uniform magnetic field. So, a uniform magnetic field B will make a particle go along a circular path whose radius is given by mv by q into b, and of course, it depends on this ratio mass by charge or charge by mass of the particle and the velocity. So, slower particles will have smaller radii of curvatures, faster particles will have larger radii of curvature. Now, from this expression for r, I can calculate the angular velocity of the particle, which is omega is equal to v by r, which is nothing but mod q b by m. So, v is r is mv by qb. So, I substituted that and I get omega frequency is this, and I can define number of revolutions. So, the particle keeps on rotating in a circular path like this, and the number of revolutions per unit time will be f, which is equal to omega by 2 pi, which is equal to mod q b by 2 pi m. So, this is frequency of revolution. So, the particle will go along circular path. So, this is the magnetic field is so it keeps circulating along a path of radius r. The angular velocity is q b by m, and the frequency of revolution is simply given by mod q into b by 2 pi m, and this frequency is called the cyclotron frequency. We will come to this later, cyclotron frequency. Please note that this frequency is independent of the radius of motion of the particle. It only depends on the magnetic field and the ratio of q to m, charge to mass ratio and the magnetic field, and independent of the radius of revolution. And this fact we will use in understanding the operation of a particle accelerator. So, there are number of accelerators which are used to accelerate particles, and we will study an accelerator called cyclotron, which is used to accelerate charged particles and that uses this fundamental property of this motion in a magnetic field, which states that the frequency, that is the number of revolutions per second of this particle, is independent of the radius of the path that the particle is following, and it only depends on the ratio of q to m and the magnetic field, of course. Now, there are a number of applications which these forces, magnetic and electric forces, find. So, I will just discuss one or two interesting applications and one or two aspects which have led to discoveries earlier. The first one is Thomson's experiment. Now, let me look at a region which contains an electric field and a magnetic field. So, let me say that I have a positively charged plate here, negatively charged plate here. So, the electric field is pointing downward, and let me assume that there is a magnetic field in this region, a uniform magnetic field pointing downward. So, there is a region of space in which I have an electric field produced by a parallel plate capacitor, a uniform electric field pointing downwards, and a magnetic field produced by some arrangement in which the magnetic field is pointing downwards. Now, let me look at what happens if I launch a charged particle from here. So, let me assume that the particle is positively charged. So, what will be the effect of the electric field? The electric field will try to push it down, because this is a positively charged particle, will be attracted towards the negative charged plates here and will try to move down. At the same time, the magnetic field, because it is now propagating perpendicular magnetic field, it will have its force, and you can see here that V cross B, so velocity is like this and B is downwards, so V cross B is upwards. So, magnetic force will be upwards. So, this will be the QVB and downward will be QE. So, this particle will have a force QE downwards because of the electric field and QVB upwards because of the magnetic field. If the particle had a negative charge, the electric force will be upwards and the magnetic force will be downwards. So, in this configuration across electric and magnetic fields, there are two forces acting on the particle. There is an electric force which is trying to push the charge towards one of the electrodes. Depending on the charge sign of the charge, it is either, if the charge is positive, this charge is being pushed down by electric field and pushed up by the magnetic field. And so, what will happen is, suppose the velocity of the charged particle is such that QE is equal to QVB, that is V is equal to E by B. If the velocity of the particle, the electrostatic field and the magnetic field satisfy this relationship, V is equal to E by B, then the charged particle will go undeflected straight, because then it has no net force acting on it. The electric force is exactly balanced by the magnetic force. So, I can use this very interesting concept to select particles, for example, of a certain velocity from a collection of particles. So, if I have charged particles with a certain velocity coming, I can use this to select particles of a known velocity. I can use this to, as Thomson did, he did an experiment to measure the charge to mass ratio of an electron, and I will discuss that in the next class. And a very interesting instrument which is based on this, which is called the mass spectrometer, which is also used as a principle to look at different isotopes in an element configuration, etc. And then we will use this to calculate, to look at some particle accelerators, primarily a cyclotron. So, let me leave a problem to you here. So, consider a solenoid of a finite length. Z axis. So, calculate using Biot-Savart law, and plot a schematic of variation of B with position along the axis. So, calculate, to take an arbitrary point, calculate the total magnetic field at that point along the axis because of all the coils, and we had actually done only at the edge, but I will leave it as a problem. It is a very simple extension of that of the example you can calculate, and I will urge you to plot the magnetic field along the axis of the solenoid. Thank you.